In this video, we're going to talk about applications of dimension. In our previous video, we talked about dimension and we referred to it as the mathematical expression that shows the fundamental makeup of every derived quantity. And some examples, we were able to do some examples. So for the sake of those that are just joining us only on this, let's just do one more example to illustrate what dimension really is. Let's use something like momentum. Momentum is given as mass times velocity. Now the unit of mass is kilogram. The unit of velocity is meters per second. If you represent it in dimension, it's going to be mass. Meters talks about length. Seconds talks about time. So this is the dimension of momentum. Let's do one more. Let's say impulse. Impulse is given as force times time. Now remember that force is given as mass times acceleration. Now times this time, we have times time. Mass is given as kg. Acceleration is given as meters per second squared times time, which is seconds. If I were to put it in dimension, we'll have mass, length, seconds is time, but there's also another second. So when we are multiplying two quantities that look alike or that are the same, we pick one of them and add their powers. So seconds talks about time, minus 2 plus 1 will give you minus 1. So this is the dimension for impulse. So let's go straight to the applications of dimension. Now, the first application of dimension is that we use it to verify if both sides of an equation are dimensionally correct. So we call that homogeneity of an equation. So what we mean by that is, let's take for example, we want to verify if E is equal to mc squared, whether it is dimensionally correct, where E is energy and m is mass. Of course, c is speed of light. C is speed of light. Now, if we in the previous video were able to establish that energy E dimensionally is given as ml squared T minus 2, and mass m, speed is in meters per second. So meters per second, talking about t, meters talks about length, per seconds t. So if we are to put it energy, we represent it with this energy, whether it is equal to mc squared. So the mc squared now, m talking about mass, this speed, remember it is squared. So we have ml squared t minus 2 equal to m. The squared is for both of them because c is squared. So this squared for l squared minus 1 times 2 will give you minus 2. So if you see, two of them look alike, so we say that it is dimensionally correct. Our second example we can look at is if energy is equal to pressure times volume is dimensionally correct. So we say where E is energy and P is pressure, while V is volume. Now, E energy is giving us mL squared T minus 2 is equal to pressure is force per unit area. Force per unit area, that is pressure. So pressure can be given as dimensionally, let's put it by the side. Dimensionally, pressure is given as force per unit area. Then volume, you can see our previous video where we derived them. V is equal to meter cubed, which is L cubed. So if we fix it here, we have that this m L minus 1 T minus 2 times L cubed. Okay, so we proceed and have that mL squared T minus 2 is equal to, here we have m, L here and L here, we pick 1, minus 1 plus 3 will give you minus 2. Then we'll bring down T minus 2. You can see that it is dimensionally correct. So let's see another one. This says T is equal to HD over G. Now where H stands for height and D stands for density. Of course, G stands for acceleration due to gravity. So the first thing you do here is to square both sides. So which is T squared is equal to 2 squared will give us 4, pi squared will give us pi squared. Now squared coming here will remove the square root, so you have times HD over G. Now one rule you need to understand is that whenever you are dealing with a dimensionless entity or a unitless entity, it becomes 1 in dimension. So we have T squared is equal to 1 times 1 squared plus HD over G. So that what you have is T squared is equal to everything multiplied with 1 is 1. Now height is in the meters and meters is length. So we say L. This is density. Density is given by mass over volume. Density is given by mass over volume. Remember, mass over volume, density. So what you're going to have is mass over volume because it is over. So we include minus. Now over acceleration due to gravity. So which is LT minus 2. If we move this further, we're going to have T squared equal to, this L can cancel out this L. So what we're going to have is L3 m L minus 3. If this T comes up, you have T minus minus 2 according to laws of indices. So that what you have is T squared is equal to mL minus 3. T minus times minus. Minus times minus will give you plus 2. So that is the answer, and it is not dimensionally correct. Not dimensionally correct. For the dimensionally correct equation, you have t is equal to 2 pi square root of h over g. This is the dimensionally correct. And how do we prove that? The same way we square both sides, we'll have t squared equal to 4 pi squared. This is cancelled by the square, so you have h over g. So you have t squared is equal to 1 times 1 squared. This is height. Height is length. So length over, we look at acceleration due to gravity. Acceleration is lt minus 2. So what you have is t squared is equal to, anything you multiply by 1 is still itself. So L cancels L. You're going to have only 1 over t minus 2. So that t squared becomes, if this comes up, it becomes t minus into minus 2. So that t squared is equal to t minus times minus is plus, so t. So you see, is dimensionally correct. So let's look at another one to verify if it is dimensionally correct. If we have s equal to ut plus half at, where s is the distance and t is time, and u is velocity, of course a is acceleration. Now you can pause the video and try out this one to see if you can get it. Alright, moving forward, we can say s is equal to, this is velocity. Velocity is meters per second, meters per second. So meters per second. So which is t. So we can say s is equal to, that's distance. Distance talks about length. So let's go straight to dimension. Length is equal to meters per second. Meters is length. Seconds, time. That is t. Every addition or subtraction sign turns to equality sign when you are doing homogeneity of equation. Always note that. So equal sign. Every unitless or dimensionless entity turns to 1. So 1 dot acceleration is lt minus 2. Time t. So L is equal to per second, L t minus 1 equals, here is, you still have one itself, multiply by 1, you still have itself. So you have, okay, we have another one. We can try s equal to ut plus half at. We want to find out if it is dimensionally correct. You can pause the video and try it yourself. Of course, s stands for distance, t time, a acceleration, and u velocity. Now moving forward, we can say distance, that is length, is equal to u, which is velocity. Velocity is meters per second. So we have lt minus 1. Time. Whenever you see addition or subtraction in homogeneity of equation, it turns into equal sign. So it becomes equal sign. So we have equals, unitless or dimensionless entity is 1. Remember, 1 times acceleration lt minus 2, time times t. So we have L equal to L. This t can cancel out this because this is over. It means it is under. It can cancel out this. Or another way of verifying that is -1 plus 1 is 0. Anything raised to power 0 is 1. So moving forward, we have this 1 times this is going to give you L. One of this will take out one of this, or you say -2 plus 1 will give you -1. So T -1. So you can see not dimensionally correct. So not dimensionally correct. For us to find the dimensionally correct equation, is giving us S equal to UT plus half AT squared. So this is the dimensionally correct equation. Now confirming that this stands for length, distance. So L equal to LT minus 1 dot T equals sign 1 times acceleration is LT minus 2 times T squared. So moving forward, we have that L is equal to, we bring down this L, this T cancels this T. So you have equal to, this L, we write it down, this T, we can write T raised to power -2 plus 2 will give you 0. So anything raised to power 0 is 1. So L is equal to L, dimensionally correct. Thank you.